Larry is the recording is starting. Larry is a professor in mathematics at the University of Indiana in Bloomington and also director of the program in pure and applied logic. And applied logic is very much a theme in his work. So I found this one quote on his website that I really much like that I shamelessly reuse here. Applied logic is applied mathematics. It's logic looking outward rather than inward. And Larry really, really lives up to this. He's a truly interdisciplinary scholar. Here in Utrecht, we have an AI program that comprises 5 different academic disciplines and know how much work it is to coordinate these disciplines. And it seems that Larry does all have it in himself as a person. So besides being a professor in mathematics, he's also adjunct professor in computer science, informatics, linguistics, and philosophy, and also member of the programs in Coxsite and computational linguistics, all in Indiana. For his background, Larry studied at UCLA in mathematics with a bachelor in 79, master in 81, and a PhD in 84. Afterwards, he was postdoc in Stanford, for a short time assistant professor in Ann Arbor, another postdoc at IBM, and then since 1990, Larry is in Indiana, and then since 2003 as a professor. To advertise Larry's achievements, I could tell you many things. I could tell you that he has more than 100 publications, including 3 scientific books and 3 textbooks. I could tell you that he had 15 visiting positions, including a visiting professorship at Johns Hopkins, visiting positions at CSLI, and here close by at the Max Planck for psycholinguistics in Nijmegen. I could also tell you that he supervised more than 18 PhD students, or taught more than 15 summer school courses, including, if I counted correctly, 5 at Esli and 4 at Nasli. I could also tell you that he is the editor-in-chief of the Journal of Logic Language Information. But for me, the most impressive fact about him is that he is among the founding fathers of 2 research fields in logic that found a lot of adepts, particularly here in the Netherlands, namely dynamic logic and co-algebraic logic. So welcome, Larry. We're very happy to have you here. We have the floor.
Okay, thanks so much for the very nice, generous introduction. I'm shrinking standing here. So let me share this. So I know people are coming in, so I thought I would make some rapport with my audience. You can see my screen, right? So I'll start with a kind of logic joke here. So one time I was asked, well, I've heard of Bloomington, Indiana. Where is it? So I was thinking of getting the map up here. Actually, Bloomington would be right about here. But this was a logic setting, and it seemed a little bit more, oops. I would like this one. And then this one. Yeah, so I actually knew what to say. This is a logic setting. So it's actually, Bloomington is the west coast of the Netherlands. So in terms of the work we do and the kind of logic environment, I feel I should be joining this VvL because this is basically the kind of logic that I'm trying to do. Okay, so I thought I would start by seeing if people remembered Watson. So if I was in person, it would be nice if people could tell me. So Watson was this computer that beat the human beings in the game show Jeopardy. So this is an American game show, and these are the experts, or the ones who won, who were the previous winners. And Watson was developed by IBM, and then became a big product actually from IBM. And it has a life of its own after that, but it made newspapers and everything. I was going to show you an example of Watson at work, but there's nothing that really, it would take a lot of time, and I think I won't do it. But if you want to look it up, you could look on YouTube and find Watson kind of trouncing Ken and Brad here, the champions, and then some interviews with people at IBM about what they thought was the main achievement of the whole thing. So I actually asked the question with some others, like what role does logic have in it? So in order to answer this, we dug up the patent for Watson. So patent means the official story on what's going on, and this is the patent's diagram for Watson. And you could see there's all kind of stuff about what happens when the question comes in and all of this kind of stuff. And these are a patent is a fairly hard thing to read. If you ever try one, it's not so clear, but you could see that actually there's no role of logic for in here. There's no explicit role for something like the work that we do in logic. I mean, there is something about evidence scoring, like what does evidence count as, and what is a hypothesis generation, what is a hypothesis and stuff like that. So I mean, this is all about language, but it's not like there's anything like prove a theorem, you know, as you're doing this and so on. So in fact, Watson is a very interesting piece of work. It's probably the largest computer artifact to date. I mean, you could, if you watch these videos, you could see that it took a small army of people with many leaders at IBM, many research leaders, and they even changed how their offices were configured at the time of the competitions. So it's someday somebody will write a nice book both about the social part of creating this and what happened afterwards, why it's not exactly taking off and stuff like that, and also what really is going inside of it. This is kind of an interesting thing. So, but the question I really want to know is why is there almost no role for logic in a system like that? Now, you might say, well, it's not really true that there's no logic. I mean, after all, the computer science at every level has logic, in the programming languages, the databases, even parts of the AI work. Every level logic is involved. Logic is sometimes called the calculus of computer science. So it's the branch of science that's closest to computer science as a workaday tool. But that's not what I mean. What I mean is that there's not an explicit role for the kinds of things that are studied in logic in the workings of Watson. If you look at the diagram and if you watch the videos of when people explain it, it's kind of there, but it's not there. So it's not there in the way that we who do logic might think that it could be there or should be there. It's just simply not really there. So that's the first kind of thing that's hanging over the talk. And so that's really what I wanted to try to understand and to try to react to and things like that. But also there's another one which is closer to like ChatGPT. So I will take it that people are not experts in large language models, but probably have tried it or at least heard of it. So this is before the ChatGPT models in October 18. So the ChatGPT was released in 2022, and in 2018, the BERT models were released. So they were, of course, developed a little bit before that, but they were released. And in the press release, they said, we open sourced a new technique for NLP. So NLP in this talk is natural language processing. It's called the bidirectional encoder representations from transformers, BERT. So it was named after BERT, and there's a whole host of follow-up ones with names that involve BERT, like Roberta, Albert, things like that. And okay, with this release, anyone in the world can train their own state-of-the-art question answering system in a few hours. That's what the press release said. And in our associated paper, we demonstrate state-of-the-art results on 11 NLP tasks. So 11 tasks in this natural language processing. And the one task that I'm most interested today is inference. So that's what I really want to know. So there's a nice article about this in Quanta magazine a year later, although BERT has come and perhaps gone. So as soon as it came, it almost was gone because better things come in this setting pretty quickly. And what was better was probably like Roberta or stuff like that. Although BERT has come and perhaps gone, it seems clear that the advent of BERT was a singularly important event in the history of AI, because for the first time, we have a computational system that can do a range of human-level natural language tasks better than average humans. That's also the background of this talk. And in fact, let me quote a little bit more. So this is from Sam Bowman, who's I wanted to quote him a few times. This is a young person in this area. He's quoted in there justly for this. Okay, so the early results indicate that solving glue, so that's something that they were trying to do, is beyond the capability. So that means that it wasn't able to do this thing called glue. But in 2018, I think by that time it was able to do this. And certainly ChatGPT and stuff like that can do this, and I'll explain in some detail what it means to solve an NLP system. The general reaction in the field was incredulity. That means they couldn't believe it. They couldn't believe it in October. Okay, this is 6 months after the April one. BERT was getting numbers on many of the tasks that were close to what we thought. This is somebody who works in this stuff and was an optimist, right? They're getting numbers on many of these tasks that were close to what we thought would be the limit of how well you could do. So that means the limits were shattered by the BERT models. in 18, and this is actually, they're actually pretty much in the dust compared to the current ones. And so this is better than anybody thought it could be. And so I want to show you what this means. And so this is actually the background of the talk is, well, what should logic be able to do? Logic, in my view, should be able to do inference. So here's what inference is. So if you have, so inference in logic is this. So if somebody gives you a list of temporary assumptions, like just you might assume it for the sake of argument, like Socrates is a man, all men are mortal. That's the most famous one, right? Or just something like in the Lewis Carroll logic puzzle or any logic puzzle. So you make a list of temporary assumptions, and then you have another sentence and you want to know whether it follows or not. What does follow mean? So one sentence, I'm going to call it H and P because that's what the computer science jargon for these is. So H is the hypothesis and P is the premise. So a sentence H follows from a sentence P if whenever somebody is competent but limited, just a real person, like a competent person, like somebody who's paying attention but is not, let's say, superhuman, if they accept the premise, then they should accept the hypothesis. So if they accept the premise, that means like Socrates is a man, sorry, all men are mortal, then they should accept that Socrates is mortal. So this is the human side of inference. So that's what it means. If a person accepts the background, so P is your background fact or facts, then they would accept the conclusion, or maybe they wouldn't. So we'll see examples of that. And then there's also going to be contradicts. So what contradicts means here is one sentence contradicts another if the same kind of limited but human, intelligent, but limited speaker would not say that they both could happen at the same time. In fact, they would say they can't happen at the same time. So here's some examples of stuff that's in this area. So what you're trying to do, so this is the task here. So this is what a computer is supposed to be doing, is you input one of these, in writing or in some kind of textual form. A flute is being played by a girl. And then you want to know, does it follow or does it contradict or is it neutral to the sentence, there's no woman playing a flute? Okay, a flute is being played by a girl. So you temporarily assume that. So let's say if I say that, I'm outside my office, a flute is being played by a girl. And then somebody, comes in and shouts, there's no woman playing a flute. Okay, does that follow? Does it contradict or is it neutral? So you should say this contradicts. Now it's a little bit of a there's this fiddly part about, well, is the girl a woman? I mean, that's a missing premise, which is standard for all of these things. But I think most people would say this actually follows. How about this one? Most Europeans are resident in Europe. All Europeans are people. All people who are resident in Europe can travel freely in Europe. So that's my premises. So that's the background. They may not be true. They may be true. But if you accept them, does it follow or does it contradict or is it neutral to the sentence, most Europeans can travel freely within Europe? So if I was there in person, I would chat with you about it. Like I would have people like put it in the chat, which I think I see somebody has done something about. No, I don't think that's exactly right. Okay, so I don't think I want to do the chat with this right now. Okay, actually it follows. Okay, it follows. So it's kind of interesting. You should say that it follows. So I see Fawn is got it. Okay. Okay, let's see. Okay, here's another one from an earlier date. So these are called data sets. So a data set means a big long list of these. So there's ones of these, and then these are fed to a computer, and the computer is supposed to do these. And usually there's a what's called a gold standard. That means an answer somehow that somebody put in. Frequently, the gold standard is wrong, as it happens. But okay, so somehow these come. Okay, both of the leading tenors were excellent. A tenor means it's like a tenor in the opera, right? Leading tenors who are excellent are indispensable. And then the hypothesis is both leading tenors are indispensable. So the answer, it follows. So I put that the answer is yes, it follows. And then here's another one. Neither leading tenor comes cheap. One of the leading tenors is Pavarotti. And then the hypothesis is Pavarotti is a leading tenor who comes cheap. So you can see, I mean, there's something to think about here. And of course, this actually is a contradiction. This should not follow. I mean, in fact, this is a contradiction. So you want to do this on the computer. Now, here's the kind of story. The storyline here is that, so the BERT model started to do this, and they were actually doing it at better than anybody else. And I'll show you what I mean by better than anybody else. But actually, this is 2018. And before that, for a few years, I would say after around 2015, maybe a little bit after that, several groups of people were trying to do this with logic. We were trying to actually use logic to do this. Now, I was one of the people. So I was one of those people. I didn't actually start to do this in order to compete with the BERT models. I actually had different motivations completely that maybe I'll hint at. But there were 3 or 4 teams that were actually, there were more than that. There were many teams of people, both in the computer science area and primarily from like logic, philosophical logic, and stuff like that, who were doing this. And in fact, the performance was somewhat mixed. So let me show you what I mean by that. Well, I'll show you in graphs. So here's what happened here. So around this time, the best stuff in the world was, I think, done by the logic-based people. And then all of a sudden, the BERT models came in, and then they immediately kind of put the logic ones, in the dustbin in a way. And so my feeling about the whole thing is that since 2018, actually, the neural machine learners are better in some kinds of logic inference than a human. That's not everything, but they're better at some things for sure. And that means that we have a really important moment in the history of logic, because this is the first time that we have machines doing the subject better than people. That's the first time in history. That's an important thing. And so I think of the work that I'm describing today as a kind of a response to that. That's how I want to think about it. Let me show you a little bit more. So this talk is a little bit meandering, so I'm making kind of side comments in between. If there were less people, I would let you ask me questions, but I don't think that this would really work with 86 of us. So the approaches to this NLI task are usually machine learning these days. If you go to a conference, actually, machine learning is the sort of tool of choice. And so why isn't logic why isn't logic the best to do this? So here are what I think are the reasons for why logic isn't. First of all, when you have logic, there's like a lot of missing facts that you somehow have to get into the computer system. Like at some point, you might need to know that girls are women, or Pavarotti is a tenor, cutting is a form of slicing, or the other way around, or various kind of facts about individual words, like kissing involves touching, things like that are not like logical. They're not like they play a role in all these inferences, but they're not like laws of logic that you would learn in a logic class. They're like something you'd learn in regular life, and unless you put it in, they would be a missing premise. They would be what in logic is called an enthymeme, a missing premise. Then there's a lot of problems about syntactic variation. So in logic, when something is proved, it's proved for sure, but that means that it has to be in a particular exact form that is strictly given to you. Like you're not allowed to mess with it. Like, for example, like I have the sentence here, like machine learning, perhaps in conjunction with other tools. If I put the perhaps in conjunction with other tools first, and then machine learning afterwards, like you can do in English, you can reorder the words. That's completely fine. But that's the kind of thing that's somewhat hard for logic, because if you're going to do this with logic, you have to translate the natural language into a representation form, and that even the translation is difficult. And for reasons that I'll get to, I'm not going to want to do the translation. And in fact, a translation to a logical form, a form with standard logic, is actually as hard as doing the inference in many cases. So that's my view of the whole thing, is that the translation is something you don't want and you can't have. So that's what I mean. But on the other hand, there are synonyms and paraphrases paraphrases are totally important. And if you try to use logic out of the box, you won't get very far because of problems with syntactic variation and things that are similar meaning. And they're just not going to, as we'll see, they won't be doing it. Then finally, I think that we're using the wrong logical tools. Usually the logical tools that people want to use are the logical tools from the standard form of logic, which is like first order logic or something close. And that's great for like foundations of math. And that's what's developed to do the foundations of math. And that's needed to do the foundations of math. And it's all great and everything else, but it's not the right tool for the job for language, because what we're doing in language on the whole is a shallow inference, which means inference like from a few premises in a few standard kinds of ways with a whole lot of background. It's not doing deep inference, which is what you need to do to prove a mathematical theorem. So I feel like it's a different task for the human being to do logical reasoning of the kind I'm talking about versus mathematics. So I really want to make a sharp distinction. I didn't put it so much in the slides, but I'll try to talk about this as I go. So here's what I mean by this is the dominant approach. So this is usually when you read a paper about this, there's all these charts about how various tools did, and you want to look at the high boldface things. So the BERT system is at 86.74 on this. That's better than the ones that are the natural logic ones above it. As we'll see, this hybrid system here is 85.95 is pretty close to 86.74, but this is still better. And there's one that's 87 here. Okay, that's even better. That's a machine learning system. There's a lot of the natural logic ones are above, and then there's a bunch of logic-based systems below. Here's what the logic-based systems did, and I want to show you one of them. So, Lasha Abziniadze, who's actually in the Netherlands, and so for that reason, I want to show you his system. He was a student of Reinhard Muskins, and so Lasha works in Utrecht these days. Use Tableau, so I want to show you his system. Then there's there are ones that translate into a richer logical form. So that is some version of second order logic or some fragment of it, something with lambda calculus. This is actually probably best done in the Japanese group, Hitomi Inaka, and Daisuke Beki, Koji Minashima, various of their collaborators. This is extremely important. And then there's the kind of natural logic one that I kind of put forward, which I'm going to end up telling you a fair amount about. But I wanted to actually start with the Tableau one to show you what it looks like. So let me put this on the screen and show you one of these. So here's this one. Okay, so this is called LangPro. So you can see this, right? So you enter in here. Every man is working. Everybody who is working has an expensive car, and then every man owns a car. So what kind of premises are missing? Well, you need to know that this everybody includes the men, and you need to know that has actually, if you have a car, then you own the car. Okay, so then you press prove here, and it's going to do the proof. So it takes a while to do this. This means that it's thinking this sort of brain-like thing here. It's thinking about it. It's doing some stuff, and we'll see what that stuff is. So basically, what it's going to do is it's going to parse this. So it parses this with a parser, which I'm going to also need parsers later. So these are parsers for what's called CCG, or combinatory categorical grammar. And then LangPro, which is the name of the tool, thinks that it's an entailment. And then it actually depends on which kind of parser you use. And here's some examples of it. You basically need to parse this stuff. I'm going to need to show you parses later, but I don't think I have time to explain how this form of grammar works. So this is the form of grammar. So these are all grammar kind of ways for the thing to think about these sentences. So it needs to parse it. And then basically what it does is it... then we want to, let's look at this one, which is now what's called a tableau. So if you know about logic tableaus, so this is a kind of representation of something about owning in cars, and it's a very long kind of deal, and you need to do stuff with this. This is a tableau, and it proves it in a kind of strict kind of way. So it actually came up with the proof. But in fact, if you actually change, you can change this. So let's say we change this to no. So we say every man is working. Everybody who is working has no expensive car. So you can just change this like that, and let's see what happens. We ask it to see if it proves it. You can enter your own stuff here, and so we'll see if it enters it, and we'll see what it says. I mean, should it be a contradiction? Should it be neutral? Should it be entailment? Okay, actually, it turned out to be neutral, so it got it right. So it is neutral. Because you could actually has no expensive car. You could have a cheap car, right? I mean, it actually is right. It should be neutral. And it's right. Just because you have no expensive car, it doesn't mean you don't have a car. So it actually does all this, and then you take a look at it, and this is a tableau, so you have what's called an open branch in it. That means you know that it shouldn't be proved. And it doesn't actually prove that it's not a contradiction. It just knows that it can't prove it in this case. So, okay, so that's what I wanted to show you about this. So this is what the logic systems look like. And let's screen. Yeah, okay. So now when you go back to BERT, I mean, there's some disagreement about BERT and ChatGPT, whether they're in effect the contemporary version of Clever Hans. So Clever Hans was a horse that could allegedly count in German. So the master of the horse's master said, oops, what is 10 and 10 in German, and the horse could dutifully click out, on this pad here, 20. But actually, it was realized later on that the horse was kind of responding to subtle cues in the master's, voice or hands or something on the person's body. So it wasn't really doing it. And in fact, so this is like what the same person, Sam Bowman, said. The same article that I was quoting said, it seems like we have a model, and a model means like a large language model. And a model is a computer program that really can learn something substantial about language, but is definitely not understanding English in a comprehensive and robust way. So that's in effect saying that there's a part of it that is a Clever Hans, but there's always a question hanging over this, is maybe this kind of imitation is the full story on intelligence. It's a very deep kind of question that comes up again and again in this kind of work. Okay, so we showed you this. So okay, so the kind of program that I'm going to try to show you a little bit about today in the next half hour is what I'm calling the natural logic program. So natural logic program is to try to show that various parts of inference in natural language actually can be done automatically. That means it could be done on the computer using surface forms. That means forms of English pretty much straight out of the box without translating to the logical system. Not even the lambdas that you saw on the tableau of the previous LangPro. It actually would like to work in decidable, so this is for the logicians, it would like to work in light logical systems. That means logical systems that are easy to study, that don't have a lot of expressive power. I would like to do this in a way that makes connections with all kind of areas of logic and computer science. Ultimately, to rework what semantics is, to rework the theory of meaning in language, coming from all this work in computational linguistics and cognitive science. So ultimately, I feel like the work that is being done should help us think about meaning again in new kinds of ways that we don't understand yet. So this is a kind of so there's two kinds of things that I wanted to show you in natural logic, and this is from a quote from Johan van Bentham. So I don't think I want to read the whole thing, but in a 2008 paper, so van Bentham, who really I think thought about this really more than anybody else in the 1980s and 90s. Basically said that really what we should be doing is you should be trying to think about inference directly on the surface forms, which means not by translating to first order logic or anything else. And it should have a few different components. One of the components should be the algebraic laws of specific items. So I'll show you what I mean by that in a minute. And then after that, there should be something about what's called monotonicity reasoning. So I want to show you about both of those, because those are the kind of centerpiece of this talk. So here's what I mean by algebraic laws. So let's think about quantity reasoning. So what if you had to reason about sizes of sets? So what's the simplest way to think about sizes of sets? I think that the simplest way to formulate as a logician the idea of sizes of sets would be to take Aristotle's syllogistic, where you have things like all x's are y, some x's are y, no x's are y, and then throw on top stuff like there's at least as many x's as y's. Just simply throw it on top. People in logic don't ever do this, because in the usual logic, you can't really say there's at least as many x's as y's in the first order logic. And since you can't say it, you don't go there. So you simply never actually ask this question. Like for students, like I ask my students, could you write down a bunch of logical laws that you could get if all you're allowed to say are the syllogistic all, some, and no, and the stuff about at least as many and as most as many and fewer and all this kind of stuff. And so, well, you can actually do logic with this straight out of the box. And what you get, I'm also going to allow you non-x's. Okay, so that makes your life much more interesting if you have just like smoker and a non-smoker, like people and a non-person. And so you write this out and you write down a huge amount of rules. But these rules are, if you give people hints, they can do this. Like, for example, let's take this one. If there's more P than Q, then there's at least as many P's than Q. Right? If there's more smokers than drinkers in my party, then there's at least as many smokers as drinkers. Then if you have more and you put the complements, it goes the other way. So if there's more smokers than drinkers, then there's more non-drinkers than non-smokers. So if you have a complement, the more flips. That's a useful one. Here's an interesting one. So the red ones are the interesting one, right? So if all P's are Q's, and there's at least as many P's as Q's. So if all P's are Q's, let's say all senators are alcoholics, and there's at least as many senators as alcoholics, let's say in a certain picture, then since they're finite, they actually have to be the same set. And if they're the same set, then all the alcoholics are senators, right? So this is depending on the finiteness here, this whole thing. This one, if I say that there's at least as many smokers as smokers as non-smokers. So if I say there's at least as many smokers as non-smokers, and at least as many non-drinkers as drinkers. Okay, then I claim that actually, what do I claim? That, well, it follows from the first one that the smokers are half or more. And it follows from this one that the drinkers are half or less. So the first one says that the smokers are half or more and the drinkers are half or less. There's only one number, that's the half. So that means there has to be at least as many smokers as drinkers. So that's a sophisticated, that's a mathish one. So you only get to do this when you ask about it. And of course, I don't think many people would say this. In fact, this one here that has 3 premises, I doubt that anybody ever has said it. But it does follow, and you can do this. You can prove that it's complete, and you can implement this on the computer, and it's in polynomial time, and you do a whole kind of stuff. And so basically, this is what I think von Bentham meant by like algebraic laws. They're not exactly algebraic laws, but they are proof theoretic laws of things like quantity reasoning. You can do all kinds of stuff like this, and it never gets to be undecidable. It doesn't get to be undecidable until you make it undecidable by importing mathematics into it. This is no problem to do this, and this is implemented. And if anybody wants to play with the implementation or teach the implementation, I could share this. But what I really wanted to do was this monotonicity, which is a more closer to this subject. So let me actually show you a video here. So I want to show you my video. Where's the video? My video should be. No, okay, let me just do this. I have to remember to let me yeah, okay. So let's put this up here. So
how can you answer a question involving words that you don't know? How can a computer do it? We'll see how, and we'll see how math enters in. Here's a sentence with some made-up words.
All the glogglfish swifferate past a yub.
And now let's ask.
Do all striped glogglfish swim past a yub?
To answer, let's take an ocean voyage to meet a glogglfish. Some glogglfish are striped. We put all this information in a scale. Up means more general, and down means more specific. They swim and they swifferate. Here is the scale of the verbs move, swim, and swifferate. Supposing I tell you about a picture that
all the glogglfish swim.
What would you be committed to? Here are the sentences that you would accept. These are what you infer from my statement. The pattern is, on the left, we move down the scale. On the right, we move up. When we change the word
all,
to,
some,
the pattern changes. And when we use the word,
no,
the inference is different yet again. It's down both times. And when we start to look at other sentences and other words, we see the same kind of patterns all over the place. The same happens with numbers. Let's look for a second at 41 minus 32. The arrows tell us that to make 41 minus 32 bigger, we can either move 41 up or 32 down. Let's put numbers and language together. In mathematics, we put things which are similar under the same conceptual roof in order to study them together. That roof is called a preorder. It's what we are calling a scale. We think of a sentence like, all big largofish swim, to be the all function applied to a noun and a verb input. The language of preorders allows us to talk about increasing and decreasing functions. Let's go back and answer the question that we posed at the beginning. What you do and what a computer could do can be studied as an application of mathematics to everyday language.
Yeah, okay, so that's my video part of the talk here. Yeah, okay, so that's the moneticity inference. I mean, that was to try to show a person on the street what this is all about. And I think that what you really want to compare this to is if you had to do this in English by translating to logic, right? I'm not saying you translate all big largofish swim into for all x, if x is a big largofish, then x swims, because I'm actually doing it directly by putting arrows on the words of the sentence and then replacing. That's the idea. So I don't know how much time I want to do on this, but let's practice this a little bit. So supposing I tell you that waltzing is a form of dancing and dancing is a form of moving. Okay, and I also told you that grizzlies are bears and bears are animals. Okay, so this is my knowledge base, and I tell you some bears dance. Okay, so we're talking about a particular place. Some bears dance. Which one is true? Some grizzlies dance or some animals dance? So one of them follows. So follow, remember, follow means if I believe this, I believe what follows from it. So the only one that follows is the one about the animals. And you can see that I moved bears up to the animals. So I would put an arrow going, so it follows that some animals dance. So that means I'm going to put the arrow going up here because it moved from bears up to the animals. So if you believe that about a particular setting that some bears dance, you're committed to having some animals dance. The inference goes up. And what happens if I say on the dance? Well, if I say some bears dance, does it follow that some bears waltz or that some bears move? Well, it follows a move, right? So the inference goes up on dance. In fact, it has nothing to do with the content words. It doesn't change if I change the bears to whatever else. And what about, so now here's your turn. So if I had more time, I would actually go through this with you. So why don't you pick one of these and try to do it? So pick one for yourself and figure out, put the arrows on the words bears and dance in all of these. This is like my homework in my class, because this is people can do this. In fact, I can give this. I've given this talk to young children, and after a few examples with even with the big largofish or with Dr. Seuss, they can do it. So if I say no bears dance, right? If no bears dance, does it follow that no grizzlies dance or that no animals dance? Well, it follows that no grizzlies dance. And if I say no bears dance, does it follow that no bears move or that no bears waltz? Okay, well, it follows that actually no bears move. So the inference goes, it follows that no bears waltz. The inference goes down. I don't know. I feel like I don't think I have time to do this, but I think people's intuitions, when you can get them to understand this, are pretty reliable. And in fact, we've done this with crowdsourcing, various kind of complicated ones. It's hard to explain to somebody what this is if they don't have a background in stuff like logic, where you want to think of, I'm not asking whether it's true, I'm asking whether it's an inference. So it takes a while for a person to understand that, but people can do this. Now, one of the interesting ones is, for example, let's see. I don't have an example with two words, the two bears in the same sentence, or two dances, but you can see here that it's not a property of the words, it's a property of the words and the grammar. Whether the arrow is not, it's not like the dictionary is going to tell you, oh, this word is always going up, because sometimes they go up and sometimes they go down. In fact, the whole thing is controlled by the logic words, like no, some, and all. In fact, what logic is actually about the inference here. It's about controlling which way the inference goes. So now this is actually similar to what you do in mathematics. So supposing I ask you, which is bigger, this number or this number? In mathematics, figure out which is bigger without using a calculator. So I would say that, so again, I'm trying to rush through this quickly, is that basically what you do is you have some ground fact, some fact that you believe, like 3 is less than 4. So that's something you believe. And then you use facts about these functions, like, for example, that negative flips. So the negative flips the order. So that's what's called antitone, or decreasing in the video. So the fact that the x is, that this is anti means you flip it. Now 2 to the x is monotone. That means it preserves the order. So that means you could stick both of those up on the shoulders of the 2, as it were. And then you do the same thing on the 7, like that. And then you finally flip it around with the minus. And this would be a step-by-step proof, from the monotonicity calculus. So we developed a monotonicity calculus that varies from the fact that various math functions are monotone or antitone, that they preserve the order or they flip the order. You can prove this, and this is a nice kind of a proof. And in fact, you can do the same thing with language. And in fact, the fact that these work the same way, this is implicit in von Bentham. It might even be explicit there, and also in Keenan's work from the 1980s. The fact that the inference generalizes, it generalizes monotonicity in the usual mathematics. This observation is kind of an important thing for the whole subject. And so now what we do here is I want to put this in a language system and do inference on the computer using monotonicity. So what we do here is we would really like a computer system that would input a sentence like some dog hit some cat, and then put the arrows on all the words. So I only showed you the arrows on the nouns and the verbs, but in fact, you could put the arrows on the some and most, and there's an equal, which means you can't move it either way. So if I say most dogs hit no cat, you can't replace dog by animal. It doesn't follow that most animals do anything. And it doesn't follow that most poodles hit no cat either, because maybe the poodles are the exception, but most of the time it happens. So we would like a language system, we would like a computer system that puts the arrows on these, and then we can use it to do inference. So this is a proposal for how you would use logic in a computational system that does inference in language. And so here's what you would do with it. You would have a knowledge base like this. So if you say dogs are animals, cats are animals, poodles are dogs, this is a form of a cat. This is wrong, but this is for, at least, I don't know if you have this in the Netherlands, but the bird was a kind of a electric motor scooter that was popular in America when I wrote this. So these all could be wrong, and they could be temporary, they could be personal to a person. Kissing is a form of touching, hitting is a form of touching, and then like every if I say something about every, it implies it for most, and most implies it for some. We could talk about all these, and the numbers are ordered in the usual way. And then basically, if you believe a certain sentence, then you could move the arrows just like the video did. So if I tell you at most 2 dogs chased at most 3 cats, I can move the 2 up, the dog down, and the chased up, to and the 3 down and the cats up, and it would be an inference. So this is a kind of theory of inference that's supposed to be kind of, roughly speaking, shallow inference in language. Because if you have the arrows, all you do is replace. You don't have like other complicated lemmas, and you don't have the individual variables, basically. So here's how we do this in practice. So here's a sentence: every cat that Fido chased ran, like that, and we hand it to a parser. The parser is what generates this tree. So this parser is the same parser that Lasha's system used. So we hand it to the parser. And the parser gives us this kind of stuff like that. And then we add to the parse. So I'm not going to go through this in detail because I don't really have time for this. And what we do is we augment it with some stuff, and we then throw in the arrows. So the arrows then get thrown in, and the arrows tell us that actually it's down in the word cat. So if I say every cat that Fido chased ran, it follows that every Siamese that Fido chased ran. And it's down in Fido. So if you know that Fido is a beagle, then if I say every cat that every dog chased, every beagle chased ran, right? If you know that Fido is a beagle, then you can move Fido down to every beagle. So there's various kind of stuff like this that I'll show you, and you could use this as a theory of inference, and this runs on the computer. So this is my PhD student, my former PhD student, who did this for his PhD in linguistics, and he wrote the programs, and we worked on this together. And so there's algorithms and computers, and you can run it on your computer. You can watch the parse. And in fact, the putting the arrows on is actually less work than the parse. So that's what a light system is. Okay, so now in fact you could do, I think I don't really have this to show you, but you could use our system to do like this one. If I say a schoolgirl with a black bag is on a crowded train, and then I say no schoolgirl is on a crowded train, it will know that it's a contradiction. But if I say a schoolgirl with a black bag is on a crowded train and I ask, does it follow that a girl is on a train? And it does. So it does this without translating this to any language, to form of language. It doesn't have to know what crowded means. It just has to know that it's an adjective, a usual adjective. If I say somebody's on a crowded train, it follows if they're on a train, right? If I say it's on a fake train, then they're not on a train. So you have to be very careful with some of these things. Okay. So now, so that's our system. So let me get back a little bit to contemporary computational systems. So the BERT system, well, to be fairly quick about it, it's extremely good at finding patterns in data. So that's what these things are like. In fact, the way I think about it is, if you need to know some knowledge base, like you need to know that a black handbag is a bag. If you need to know that being on a crowded train means you're on a train. If you need to know that a train is a vehicle. If you want to know that Pavarotti is a tenor. You basically have that for free when you're dealing with a large language model. And you have anything that could come from a pattern. Now, the facts about monotonicity, about those arrows, are fairly complicated to write down. So like, this is where my math training really came in. I had to write a paper about the mathematics of this in order to get to prove that the system was going to do what it was going to do. It's a fair amount of mathematics. But once you know that, then basically a large language model can find all the mathematics as long as it's simple enough. That's basically what it's really good at. As soon as it's reasonable for anything to find what you're dealing with, the large language model is going to find it, but it's not going to know what it's finding. It's not going to have any theory of knowledge about it. And in fact, I'll show you what that means in some detail in a minute. This is the way the large language models work. Here's how our system works. So we saw how the Watson had an architecture. This is the architecture of what's called monologue. So this is what Hyde developed for his dissertation. So you have premises in a natural language, and you run it through a parser. Now, the parser, you might actually need some help on the syntax. That turned out to be fairly important. So that means you might need to reformulate what you're doing in the natural language. Then we have the CCG to mono is what puts the arrows in. So putting the arrows in gives you what I'm calling polarized parses. Oops. And then you have natural logic, and you have monotonicity, and you have a few other kinds of things, all of which were envisioned actually by von Bentham. Basically, you basically have all those kind of stuff, and you have a kind of a calculus of how you're going to do the inference, and you have a knowledge base. The knowledge base is usually something like WordNet or something light. It's not as good as the knowledge base of a large language model. And then you have an inference engine, something that does the inference, which is usually just a fairly easy thing to implement and stuff like that. And then you get your output. So how does it do? Well, I think I showed you this one before. Out of the, if you add some stuff to it, you add some linguistics, that means you're adding some extra linguistic things that we didn't think about before we did this. You can get up to like 81% on a certain data set that at the same time the BERT was getting at 86.74. At some points, you might want to like ask BERT for help. What does that mean? You might like to ask BERT for help if two things should mean the same thing. Or you have a kind of hybrid, which means you're going to like add some features of what we did with some features of what a large language model can do, and it almost does as well as this one. So that's something to know. In fact, if you do something a little bit better, so these were done by 2 undergraduates at another university in Indiana, Rose Holman, which is a very good engineering school, and these were star students who in the pandemic started to come to my classes on Zoom and actually took what I did and changed the parser from CCG to what is called a universal dependency parses, and they improved the system in several ways, but actually it's improved, but yet it's not mathematically as understandable. So I proved a whole lot of theorems about the algorithm, and what they did was they said, oh, the algorithm should work like the following on this other form of grammar, but this other form of grammar is not like a mathematically specified thing in the same way. So I don't in some sense understand it, but it works better. And in fact, if you look at this actually, this system actually is the best in the world on this data set. So by the last time I looked, this is getting 90%. So this is better than the BERT system. So in fact, this the stuff that they did and implemented is, at least it was the last time I looked at it, was the best on this particular data set called the SICK data set. And so they basically, here's their scheme. It uses a different arrow tagger. It uses a different parser. This is the standard parser or something more like it in computational linguistics. It uses the BERT system with paraphrase, so it had a better improvement on that, and so because of that, it did better. And here's a whole lot of stuff that we did in this. Should I take this? I think I don't want to show you this one. If anybody wants to know what we've been doing with this, I can talk about it. But let me actually end. So I want to talk about this follows from in a very big kind of way. So here's like the question is really that I'm dealing with is inference. Like, what does it mean for one thing to follow from another? In some sense, I think of this as like the holy grail of a number of fields of study. And in order to make progress on it, a lot of fields actually give up something. So for example, in linguistics, you basically give up on inference. So they never talk about inference in linguistics semantics. They talk about truth conditions, but they don't actually really ever get to the question of when one thing follows another. In logic gives up on real language. Basically, in a logic class, you can teach somebody how to symbolize something, but then you don't ever do anything with that. You basically don't ever go there anymore. So in fact, you give up on this idea of real language when you're doing logic. In psychology, you actually give up on anything complicated. So there's a whole branch of psychology of language that's all about syllogistic inference and why do people do certain things right and not right. So in order to get that subject off the ground, they restrict attention only to the syllogism or something fairly close. So they give up on anything complicated. Well, good old-fashioned AI, so that's AI in the logic sense, actually gives up on anything having to do with people, because you basically write down the rules of everything. You supposedly write down the rules of everything that could possibly be true. You give up on human competence and you throw everything into first order logic or something worse. So you're giving decidability in some sense. Giving up on strictly logical inference is what machine learning does. So machine learning actually gives up on grammar. It doesn't have grammar in it. It doesn't have semantics. It gives up on everything, and it uses data only. So basically, the idea of contemporary machine learning is to think about inference, but only based on data. So for example, this is from our current work. So I really will finish up very quickly. So if you ask a premise from a math paper, we compute some simple examples and explore the elementary properties of these invariants. So this is from a math paper. And then you ask, does it follow? We explore the elementary properties of these invariants and prove that no other invariants exist. So should that be an inference? Should it be neutral, or should it be a contradiction? If you think about it, just because you proved something doesn't mean you prove that nothing else exists. So it should be neutral, right? I mean, if I say that, I proved a theorem about, I studied circles, it doesn't mean that nothing else exists. So that's just not really right. And so the ChatGPT or Llama or one of these other systems actually said it was a contradiction. And we asked, could you please explain your reasoning? So you can actually ask them to explain the reasoning. And you explain the reasoning, and from about up to here, basically great reasoning. And then after that, it kind of goes off the rails, and it ends up by saying it's a contradiction. Because basically it says, this one, like the hypothesis, by claiming that no other invariant exists, introduces information that contradicts the premise. In fact, it doesn't contradict the premise. It actually is neutral to the premise. So it's beautiful. It's a very beautiful prose. It's completely wrong. Usually these things are right, and they give a very nice explanation. But in fact, it's giving you this as it were, word for word from some other sources. It's not giving you, it understands anything of what's going on. So that's why I'm saying that in fact, what I said was it actually gives up on everything. It gives up on logic, on grammar and semantics, and uses data. But of course, it does a nice job. It just doesn't do a perfect job. And so that's what, so I think all these things give up on something. And what I'm trying to do, so this is my team on this, that is doing this work, especially Valery DePipo, who's thinking about mathematics and with all this stuff. And my team includes Qubin Gao and Hai again, Pavel Kovalev and Yikai Liu back in China. So I would like to do, so here's what I think is the place of logic in contemporary studies of inference on the computer. I think we should put inference at the center. It shouldn't be like a secondary matter. It should be the center. You should really, that's what it should be. So in all of these studies, it's there, but it's there in a partial way. In linguistics, logic itself is about reasoning. Certainly in AI and cognitive science are partly about reasoning. In math, somewhat. In philosophy, definitely. In rhetoric, for sure. But in natural logic, I would like that to be about all of these things. And I actually think that we should be putting all these things together. And we should also be trying to find new forms of logic, like I was trying to show you with this, the reasoning about quantity, and also with monotonicity reasoning. And if you really want to know what I have to say it's a fairly difficult question about whether algebra means just structure, whether structure has any role to play in contemporary language, which Shalom Lapin and Jean-Philippe Bernardi put together a book, with people's opinions about this. And so my opinion was that algebra and logic we have reasons for content, we have reasons to be happy, and we have reasons to be unhappy. And if you want to, you could ask me about this or look at this. I mean, as you could see, I'm on both sides of this. And so I wanted to thank everybody, especially Dominic and Antoine for the very kind invitation to talk to you all. And I look forward to hearing from Natasha and Bart, and to actually helping everybody for helping me learn more about this today.
Thanks a lot. Thanks a lot, Larry. And I think it would be nice if you could just give him a round of applause by all unmuting ourselves, and we can give some real applause for a second. So. Great. Thanks a lot. And as Larry mentioned, the further program is going to be that we first have 2 commentaries by Natasha Lechina and Bart Verheij, and afterwards we'll move to the general discussion. And I think our first commentator is Natasha. Are you? I think she is unmuted. Yeah. Yes.
I have unmuted.
Perfect.
Uh,
I can quickly introduce you if you want. So it's Professor Natasha Alekina. Very happy that she joins us and gives her comments. Natasha has a chair for safe and responsible AI at the Open University in the Netherlands and is also at the same time associate professor at Utrecht in computer science. She works on using logic for a broad number of tasks, including safety of programs, specification, verification, and synthesis of multi-agent systems. And I think lately she also became interested in the relations between symbolic and sub-symbolic AI. Natasha holds a master's from Moscow State University and a PhD from the ILC. Afterwards, she spent some time in the UK, first as a postdoc in Birmingham, and then close to 20 years in Nottingham, first as an assistant and as associate professor. And then in 2019, she moved back to the Netherlands, first to Utrecht, and then last year to the Open University. Natasha has more than 100 academic publications on a broad range of topics, including causality, norms, belief revision, strategic reasoning, and many more. She's on the editorial board of Jolly, so the Journal of Logic, Language Information, and Autonomous Agents and Multi-Agent Systems. And she also co-led special interest groups or led special interest groups on autonomous intelligent systems and neurosymbolic AI. Welcome, Natasha. I give the word to you.
Thank you very much. Thank you for a very kind introduction. And Larry, thank you very much for an interesting talk. It is a really impressive program of natural logic and extracting it from language. Or understanding language using this sort of prism of natural logic. It's also very brave because, as you say, you kind of have to give up on what logicians like to anchor themselves on, like it is correct. These are valid rules. If I reasoned like that, I would never make a mistake. So instead, as far as I understand, you replace it with just any reasonable speaker who accepts the premises, would accept the conclusion. What do you think? How far can you push this sort of vague criterion of correctness or validity or goodness or whatever we want to achieve with this kind of natural reasoning?
Okay, shall I answer this now and then we take, yeah. Okay, so first before I start, I actually wanted to make a slight correction to Dominic's intro of both of me and Natasha. So Natasha actually is the editor of the Journal of Logic, Language Information. So she has taken over from me. So she is the editor. so I'm a has-been. So she's the editor. So okay, yeah. So you're that's a very important point. In fact, when I do all this stuff, I have a kind of semantics in the background. So everything is absolutely right up to some assumptions. So like I wrote down, you have a knowledge base. So if your knowledge base said that hitting is less than thrashing, or thrashing is less than hitting, that's your assumption. And if you make your assumption, and you do all this stuff in my system, it's sound, which means you have to believe that it follows. So the part about human inference is a kind of my wish for the whole thing, but I don't actually ever get there because I don't really know how to deal with that. So in fact, I'm kind of, the work is on the side of, well, it's more like the logicians' approximation to like the human inference. The actual thing about human inference is very difficult. Like when we looked at the sick data set, a team of us, I think I put many of their names there, actually went through all 10,000 of the examples, or all the examples that we thought were problematic. And we went on Zoom for a couple of years and fought about them. Like if I say, let's say I'm holding a dish, like if I say I'm holding a cup, does it follow that I'm holding a dish? Like, does a dish count as a cup? Does a tomato count as a vegetable? Scientifically, actually, it isn't. It's a fruit. Various kind of things like that are is a bat a bird? In traditional medicine, a bat is a form of a bird, but in modern science tells us a bat is a mammal, so it's not a bird. numerous questions like that, or things of opinion, and it's very hard to know what to do, because even the people who are doing this for years and years disagree with each other. And it's extremely hard. And then there's also whether you're doing it as a logician or whether you're doing it as a person on the street. Like if I ask myself that, is slicing a tomato, does that imply cutting it? Or maybe I sliced it with a saw, or maybe I sliced it with some other machine that didn't cut it somehow. Or if you do it with as a logician, you're going to basically have very few things that are absolutely inferences. But if you do it as the person on the street, then you get a lot more, and then you have to wonder, well, what is really going on? And maybe there are times when you read the premise, when you read the sentence that you're asking about, you change your opinion about what you're talking about. That happens a lot. And then you're wondering, well, is that what you're supposed to do in this? What is this inference? And so in fact, I find that there's a lot of deep questions about language and meaning that come out of looking at many examples of this. You start looking at this, you actually would find that we don't really understand this inference as well as we would like to. That's what I find. Is that an answer?
Yes, but I have a follow-up question. So I totally take your point about is a cup a dish and is a girl a woman, and it's quite clear that it's just a matter of kind of sorting out what we mean by things. That's not logical inference. It's just understanding the language and agreeing on terminology. But when it comes to the actual logic, these little rules that if something is down, then you can substitute something that you agreed is less. So that is actually has a sort of formal semantics and formal definition of correctness.
Absolutely. It's actually very interesting kind of mathematics as it happens. It actually based on the theory of higher order preorders and uses some fancy mathematics. And I'm very happy with it, and it's sound, and we don't have anything like completeness for it, but I would like to. And there's algorithms, and there are open questions, and yeah, the whole thing is sound. It's a done deal. It's really there. It's not a matter of opinion. Yeah.
Okay, good, because at first I misunderstood that that's all we have, that if a person accepts it, but obviously a person could make a mistake.
That's right. Yeah, I'm trying to have it both ways, and so I was caught.
Okay, maybe I should give a turn to Bart.
Good. Yeah, as Natasha said, our second commentator is Professor Bart Verheij, who is joining us from a research visit currently in France. He's taking a break, especially to talk to us here. Bart is professor of, and now I'm losing my notes, holds the chair of AI and argumentation at the Rijksuniversiteit in Groningen, where he's also the head of the Department of AI at the Bernoulli Institute. He works on knowledge, data, and reasoning with some special interest on legal reasoning. And indeed, he has a very interdisciplinary background, master's in mathematics, and then a PhD joined between the law and the computer science department in Maastricht, defended in 1996. Afterwards, he was assistant professor in Maastricht for a while, before then moving to Groningen in 2004, where he became a full professor in 2022. Bart has more than 160 academic publications, including 4 books and 2 textbooks, and has supervised more than 15 PhD students. He had a number of visiting positions, including having been resident fellow at Stanford, invited researcher in Cambridge. He's the editor-in-chief of Argument and Computation, and he was president of the International Organization of AI and Law. Besides this, Bart has been involved in a number of very, very big research projects, such as an NWO's Vaterkracht Hybrid Intelligence Project, where he co-coordinates the Responsible Hybrid Intelligence Group. And he has led a project on the connection between arguments, scenarios, and probabilities in forensic reasoning with evidence. So welcome, Bart, and you have the floor.
Thank you. I've prepared a few slides. I hope that I'm successful in sharing them. Are they now being shared?
Yes.
So very nice talk, Larry. It's a pleasure to be interacting with you with also this very nice audience, and Natasha. Thanks, Dominique and Fan. So when I see your title, I think of reasoning in artificial intelligence, right? So reasoning is, let's say, the informal version of what logic is all about. And computer processing of language, well, that sounds like being at the heart of artificial intelligence. And because of looking already a little bit beforehand at your slides, I was thinking of the history of reasoning throughout artificial intelligence. And I'm curious whether you want to also perhaps comment a little bit on that. So it started with rule-based systems where, let's say, reasoning is forward or backward chaining, and the reasoning has a clear position. Then we had non-monotonic logic, which was aimed to be about incomplete, inconsistent, and uncertain information. But well, whether it was really computational step-by-step reasoning, that became a bit problematic. I like to think a lot in terms of computational argumentation, where the arguments are constructed and then evaluated with all kinds of semantics. In ontology, semantic web style, you have class inclusion and consistency checking. That is the focus of reasoning. Bayesian networks also sometimes have a claim to reasoning, but that's only probabilistic updating. And well, at least some of us think that that is also reasoning. And reasoning as feed-forward information flow. If you are kind to neural networks, then that is also a form of reasoning, but we can have a discussion about that. And now suddenly we have the large language models that you spoke a lot about, at least hinted at. And they suddenly have textual output that has reasoning expressed inside them. So that brings me to this list of discussion points. So sometimes they seem to reason. Is language technology now really unexpectedly closing this knowledge data gap in AI? And why is that then? Is it accidental emergence, just magic, so just something that we have discovered? Or is it the data? Is it the architecture? And how can we even find out about all this? Is there science behind all this? Or second question, should we focus on monotonic formal reasoning or on other kinds of reasoning? Maybe those that are more arguably better aligned with everyday inference, maybe non-monotonic exception, blah, blah. Where to start? And the third one, will the reasoning behavior of the large language models help them perhaps become better aligned with humans? Are we entering a new phase in the responsible use of AI? Maybe finally again having something that we can trust? Because that was true in the days of logic-based AI. Well, that's my commentary.
Okay, these are incredible questions. And,
yeah, just as maybe also for the audience, but I know that you have a lot to say about that.
I mean, I have something to say, and I would like to know what you have to say. But I can make a few comments. I mean, to some extent, my feeling is that in logic and actually in everything else that you listed before, we basically ignore this learning. And so the learning is what is done in machine learning. And so I feel like because we ignored it for so long, we don't actually have anything interesting to say about it, but that's what we should be thinking about. So you know, your first question, I can't say that a large language model is closing any kind of a gap like that. But what it's doing is highly interesting for the study of inference, and the fact that it does better than you would expect, or than anybody really had a right to expect when it started, and let's say the BERT models, is an important thing going on. So it's important. Whether it's going to actually close this gap that you refer to, I kind of doubt it. But then again, I've been wrong about everything else with this too. So what was the second one you had asking about? You were asking about, so maybe put those back.
Monotonic formal reasoning, or maybe also other kinds of reasoning.
Yeah. So in fact, I agree with that.
Just very quickly, maybe you can actually put up the slides, or alternatively post your questions to the chat if you want, so that also others can refer back to them. I think it would be helpful.
Yeah, I actually think that that's right. And in fact, one of the things that all this work on inference kind of highlights for me is the need to think about inference that people do in the light of something bigger than inference. So I think of, well, what I'm trying to do, it really is monotonic formal reasoning. That is, so I'm doing on number 2, focusing on monotonic formal reasoning. So all those logics are monotonic. But I actually think that thinking about non-monotonic logic again is a good thing to do. So I think that we should broaden it. And we're pretty close to having something interesting about monotonic formal reasoning, and then we should go on to something else too. And then will the reasoning behavior of large language models help them to become better aligned with humans? I mean, time will tell on this. I don't know that I can have anything really great to say about number 3. I mean, to some extent, we are trying to think about this with the work on mathematical reasoning, just as one example of reasoning is to focus on one kind of domain and to try to see what large language models do and how they explain it. And I guess you might say we're trying to see whether they could be aligned with human. I feel like nobody has asked me, or nobody has brought up yet, there's like a million papers on trying to find out what the capability of large language models is and how you would improve them. I think we're still working on that. So I don't know. I don't think I want to say that it's going to work. And in terms of responsible use of AI, of course, just like with learning, you won't get it unless you try to do this. So if people want to work on responsible use of AI, they should make that front and center what they do. It won't happen by itself. It should happen, right? And it won't happen by itself. So I don't feel like the reasoning I don't feel like work on reasoning is like important in that. It's like something, but I don't feel like it's, if you want to do the ethical part of AI, then that's what you should be thinking about. And the part about the reasoning will sort of take care of itself. That's my guess.
Yeah, so because if the reasoning is at least reliable, like what logicians focus on, right? That is also part of responsible use, right? So databases, we know how they work. What you see is what you get. And that is not now, or so it seems, with the machine learning systems the case.
Well, that's because they hallucinate. They hallucinate their answers and they make up their facts and stuff like that. Yeah. So yeah, okay. So in that sense, yeah, I agree with you that we need to get correct by construction algorithms with large language models that don't hallucinate facts, that don't do, like what I showed before was a kind of hallucination. It kind of like said something was a contradiction when it wasn't.
Mm-hmm.
So
interesting. But I saw that Natasha has very strong opinions, so I don't know whether she's allowed to say something.
Natasha, yeah. We can't do so.
Yeah, okay. Yeah, I got rid of the hand. I just wanted to make a couple of points. One is that indeed large language models are not doing reasoning in a sense of they have a rule and they follow the rule, and in the sense that Larry is doing reasoning with arrows or anything else. There is also slightly confusing factor that there is this chatbot wrapper around the large language model that you can kind of help along a little bit with this and that, and ability to count and ability to do a Google search for facts and things like that. But and they're getting better and better in combined facility. I just put Larry's last example about invariance into the ChatGPT 4o, and it said that these two sentences are not kind of related in any way.
Oh,
not contradictory. Yes, I can send you the.
definitely.
But it's not proving anything. I mean, these things are amazing. They have very impressive performance, but you can't trust them to say true things because they have no idea what's true and what's not. They have no notion of fact. They just know what they read, and that's it. And they read lots, and some of it is complete nonsense. And they're trained and sort of helped along to sort of do more and more and more step-by-step reasoning, but you can never be sure that they're correct. So I think that they certainly made AI much more accessible and interesting and occasionally useful for everybody, not just researchers. But you shouldn't be using them for anything safety critical, just even kind of potentially damaging, that they could upset people because they don't know what they're talking. They increasingly are told to say, no, I don't know. That was a big breakthrough, because before they hallucinated almost by necessity, because when they didn't know what to say, they just made something up. So increasingly ChatGPT is not doing that. Again, that's a wrapper around the model. The model is just the same as it was before. So that, sorry for the rant. I just, well, it was a very nice question, but
right. And maybe on this, or unless one of the panelists want to have a final word.
Oh, please, Dominic.
If not, it's maybe time to open our discussion also to our broader audience, which means that now would be the moment that the recording stops. The general